Hello everyone, welcome to Unacademy. And guys, it's been a while since I haven't posted, but yes, we are now going to continue our reaction series. This is our 25th reaction, that is the Nazarov cyclization, and we have targeted 100 reactions. So definitely I hope that you are also learning along with. As soon as I post the reaction, I hope that you see it and practice it and also share it with your friends, because this is free knowledge, and definitely it must reach out to everyone. Alright, so as you can see, I have taken some bullet numberings over here. Why? Because we have something very important to talk about the Nazarov cyclization. So guys, this reaction looks like it's a very simple reaction, okay, but there are so many things about it. That first of all, it is a simple acid-catalyzed electrocyclic formation of cyclopentenone from divinyl ketone. Alright, so what do I say? Yeah, what is this basically? Acid-catalyzed electrocyclic reaction. So this is some kind of cyclization reaction catalyzed by the acid. What are you getting? You are getting di from the divinyl ketone that you see over here. This is your divinyl ketone. Okay, see the divinyl groups and the ketone. So from the divinyl ketone in the presence of an acid, you are getting the cyclopentenone, ene and one. Okay, so this is the overall reaction. The acid could be your protic acid, or it could also be Lewis acid, and we are going to see the examples of all of these. Yes, so basically there are two more important points about this reaction that we are going to quickly discuss. Now, desilylation is generally preferred over deprotonation. What is this point? We are going to consider this in the second example, right? So desilylation is generally preferred over deprotonation, and the known cation stabilizing effect of a silyl group helps to reduce side reaction resulting from the intermediate allyl cation. So what is this whole sentence that we are going to see in the example? I just want you to know for now that there is also a possibility of desilylation. For example, you know already that the polarity of silicon and hydrogen, both of them is positive, right? So they are positive polarity groups, so they behave in the same way. Just that there is one additional factor about silicon, that it is able to stabilize the beta silyl cations. That is the most important thing. It is able to stabilize the beta silyl cations, okay, and that gives you a particular product. And ये देखो यहाँ लिखा है it reduces the side reactions, right? So what are those side reactions which are possible? That also we'll see. Now the last and the most important point, that Nazarov cyclization is a 4-electron cyclization and occurs thermally by a Kohn rotatory process. So yes, did we see electrocyclic formation? Yes, acid catalyzed electrocyclization basically. So when 4 electrons are involved, and when the reaction is carried out in the presence of thermal condition, 4n thermal goes to Kohn rotatory. You know this by the Woodward-Hoffmann rule, isn't it? Yes. So we are going to see what is the stereochemistry of the groups after a Kohn rotatory process, right? So let's talk about all of these points one by one. Okay, so the first one is just looking at the mechanism. So first, the overall reaction is like this, as we already see that, okay, in the presence of acid, it could be a protic acid or a Lewis acid, you are going to get the positive charge on oxygen like this, and then there is going to be cyclization in this manner to give you the product. Okay, now cyclization could be a two-way process, alright. You could also get a product like this. Okay, so that is why we need to understand what is the mechanism. Okay, so here we move onwards about the mechanism. What is happening? Let's see. So in the presence of an acid, definitely your carbonyl has n electron pair, okay, alright, non-bonded electron pair, which is going to grab the proton or the acid from the medium, and there is going to be a positive charge on the oxygen, which is relieved which is relieved by opening up of the pi bond of the carbonyl group. And then what happens is, then one of the pi bond is going to move. Let's say this bond moves, okay, and that is going to give us this reaction over here, this part of the reaction, like this. Okay, so you are going to get a carbocation in this manner on this carbon. Okay, and further loss of this proton gives you an enone system, basically, which I am writing. So that is going to give you an enone system like this, OH and a double bond over here. Now you see that there is tautomerism possible. Yes, it is tautomerism which is taking place over here. The enol group could now be converted to the carbonyl keto group like this, and the double bond remains as it is. The other question is, we might also have the cyclization in this manner. If we start from the same intermediate, let's say we are starting from the same intermediate, the cyclization could also possibly be like this. Okay, that gives you a carbocation. Let's say this is OH and the double bond moves over here. Let's say that gives you a carbocation over here. Alright, so both of these are possible. Both of these are possible reactions. Now the proton over here, it's lost on the alpha carbon right here, and it is going to give you the alkene onto the cyclohexane, right? So this is your product. So you could have two isomeric products from the Nazarov cyclization when you are doing deprotonation. This is what I'm talking about, deprotonation. Where is the deprotonation? So you know already, in the first step there is the protonation of the oxygen, and the cyclization takes place in the second step, that is right over here. Here is the deprotonation step that gives you enol system and a double bond, or finally tautomerizes to the enone. One of the possibilities. Yes, the other possibility is that again you have the cyclization from a different manner. This proton is lost to give you another molecule, another enone system like this. Again deprotonation happens. So in one of the bullet points previously studied, what did we study? That desilylation gives you less of the mixed products, or let's say more specifically you're going to get one product only. Okay, so over here also in this reaction it is shown that this one is our major product. So finally I have written only one over here. It is shown to be experimentally given that it is our major product over here. Now yes, let's talk about this example. Okay, we have already seen one of the examples. Now this is our second example. Let's talk about this. Again, whenever you see a dienone system, isn't it a dienone? Yes, this is dienone system, right? So whenever you see a molecule like this, you are able to, yes, in your mind you are able to do this, that there are again two possibilities of carrying out the same reaction. What you can do is, the cyclization could take place in this manner or the opposite manner also. But here, since we are having a silicon group, there is only one method by which we are doing the cyclization. Okay, that is the same thing that I have done over here. Let's talk about this as well as the other one, since I told you there are two methods. So chalo, first of all, let's understand this. There is a nitrogen. This is an added point how we can define the reaction. Otherwise, even if there was no nitrogen, the reaction would take place in this manner only. Yes, why is that so? Alright, so in the presence of again, it could be a Lewis acid also, it could be a, let's say over here you have a Lewis acid, very well. So it could be a Lewis acid, it could be a protic acid. So let's say we are having the Lewis acid over here. Okay, so this is how you are going to get the carbocation formation beta to the silicon. Now this is our beta silyl cation. We can understand this mechanism by two ways. What are the two ways? That okay, the the cyclization takes place in this way, and there is no role of the nitrogen as such, only that we are getting the beta silyl cation, which is thought to be more stable. Why is it more stable? Because yes, why is the alpha silyl cation not stable and the beta silyl cation more stable? Because here it can do hyperconjugation. What kind of hyperconjugation? The silicon methyl bond, the silicon methyl bond can do hyperconjugation to the beta carbon. That is not possible for the alpha one. Alright, yes. So the other thing that I was showing you over here is, let's focus that there is one more way of showing the same step, that when you have a nitrogen, the nitrogen is going to assist in this reaction. The nitrogen is going to assist in this reaction, and this way you get your intermediate like this, a positive charge on nitrogen, oxygen, Lewis acid, double bond, silicon SiMe3. So now there is a positive charge. Now this bond could be moved and you can still get the same intermediate that we started from, the same beta silyl cation, isn't it? Yes. Now what is the fate of this beta silyl cation further? After the beta silyl cation has formed, let me just focus on the beta silyl cation over here. Okay, let's talk about this only. Yes, so if we have the beta silyl cation, what is going to happen further, right? Okay, so here we are after the beta silyl cation formation. Since we have a Lewis acid which is going to get connected as zirconium, there is going to be a bond formation. It's not just the interaction, there is one bond formation. So we can write that one of the Cl minus gets free from zirconium, and that Cl minus could attack the silicon, since it is a good nucleophile, not a good base. Okay, and you can get the desilylation. This is what we were talking about, isn't it? This is desilylation. This is an alternative to the deprotonation step that we have done. Yes, you get a double bond over here, you get an oxygen connected with the Lewis acid. Now this is your molecule. Further, after hydrolysis, let's say you are getting the enol. Yes, after the hydrolysis you are getting the enol in this manner, OH and a double bond over here, and it is going to undergo tautomerism to finally give you the ketone. Now the question is, how are we going to explain the stereochemistry? Both of the protons are above the plane, or basically even if it is above or below, you have to understand that it is a cis junction, right? These two carbons are at the junction of the two rings. It is going to be a cis junction, because a 5-membered ring is a small ring, and definitely it is going to prefer forming a cis junction. Okay, so when we did the cyclization, let's say the hydrogen goes above. It could go below also with equal possibility, but let's say it goes above. All right, yes, it goes above. Now in the next step, that is final step, where we are getting another proton on the junction, this is the tautomerism step. All right, so the proton could be transferred on the above to favor a cis junction, right? This is always favored for a 5-membered ring. 5-membered ring cis junction. So this is how we explain this reaction, and you get 76% of this yield, right? It's a very, very important reaction. The step desilylation, let's go back on to what we have taken. Desilylation is generally preferred over deprotonation, right? And we proved this. And the known cation stabilizing effect of a silyl group, that is the beta silyl cations, helps to reduce the side reactions resulting from the intermediate allyl cation. Now what is the side reaction? Let's also talk about that. Okay, I'm just clearing out a little bit. So this is your major product that you saw through this mechanism, through this cyclization. What are the side products that are possible? Let's talk about that as well. So here we are. Again the same molecule, again there is going to be, or let's say there is a bond, ZrCl3 now, oxygen P positive, and the other possibility is that you are getting this bond moving like this. Okay, and that gives you something like this. This is the other possibility, or let's say the less favored possibility, I would say. Why the less favored possibility? A double bond moves in this direction. Trimethylsilyl has now a positive charge on this carbon. There is a positive charge on this carbon. Now this is the alpha silyl cation. Alpha silyl cations are unstable. Why are they unstable? Because silicon does not have a lone pair. It does not have a lone pair to stabilize this positive charge. Only those elements, let's say oxygen, nitrogen, and so on, who have a lone pair, let's say, alright, who have a lone pair, they are only able to stabilize the alpha cations, not the silicon. So this is a poor possibility. This way cyclization goes through a less stable intermediate. Yes, this cyclization goes through a less stable intermediate, and hence it is not happening. Or let's say even if it happens, yes, we are again going to do deprotonation because there is a positive charge on this carbon. Yes, okay, just a second. Positive charge over here. Positive charge over here, and a hydrogen has to be lost from this way. Yes, to get the deprotonation, to get this product that we have, where decellylation does not take place. Alright, so it is not the decellylation which has happened, it is the deprotonation in this step, and you are getting a side product in this manner. After the aqueous workup, you get the enol and the corresponding ketone group. But this reaction is definitely not happening. This product is definitely not forming because first of all, it goes through alpha silyl cation, okay, which is very unstable. The second thing is decellylation is more preferred also as compared to deprotonation, since you are having in this case, since you are having a Cl minus as a free anion, and you know it is a better nucleophile, as compared to a base. It is not a good base because the pKa of HCl is very low, very low, less than 0. Alright, so it cannot be a good base. So that is why deprotonation for this does not happen and decellylation happens. Alright, let's now consider one more reaction. Now about the stereochemistry. Here we are talking about the stereochemistry. Alright, what stereochemistry, guys? Basically, in the last step that we had talked about, that okay, it is a electrocyclic process, electrocyclic 4n pi electrons and con rotatory process. Now how are we going to understand that? Because in the product, if you have noticed enough, in the product you get the enone system. Basically you get the enone system like this. So we are not able to understand the stereochemistry of this reaction, that whether it is a electrocyclic process or not, and what is the stereochemistry, is it coming from the con rotatory or disrotatory, that we are not able to understand, right? But let's say we want some clarity on geometry. What can we do? We can modify the reaction a little bit, and the last step which makes this double bond is either the decellylation or it is the deprotonation. We can avoid that step. If in any manner we can avoid that step, then we will be able to, yes, then we will be able to get the correct geometry. Alright, let's talk about that. I hope that what I'm saying makes sense to all of you. Yes, so we are avoiding the deprotonation or the decellylation step. Right, let's move onwards. So we look at this molecule and we see that there are two phenyl groups and if they move in the con rotatory manner. So drawing it like this, guys. If two of these phenyl groups are moving in the same direction, con-rotatory, then after the ring closing takes place, one of the phenyl stands up, the other phenyl goes down. So we can surely say we are getting a trans geometry. Alright, so let's look at that if we are getting a trans geometry or not. So in this case, we are using boron trifluoride, basically a Lewis acid BF3. Okay, and it's going to we can directly write like this also, because ultimately you have a positive charge on this carbon that gives you an intermediate like this. So I have taken this example directly from Caruthers, and I hope that you follow that book. Okay, so here we are O minus BF3. Alright, and there's a methyl, there's a positive charge on this carbon. So any one of the bonds can rotate, or let's say we are directly doing the cyclization process. This is also a cyclization process only. Now you understand, first of all, in the cyclization only we are getting the trans geometry. In the cyclization step only, in the cyclization step only we are getting the trans geometry. But how are we not able to find that out? Because in the last step we are having deprotonation, so we are going to avoid deprotonation in this reaction. Alright, so let's say there is a positive charge on this carbon after the bonds have moved, and this is what you have, let's say. Okay, so ultimately how are we avoiding deprotonation? Because we have added triethylsilyl group, and the triethylsilyl, basically triethylsilane, is going to get attacked by the oxygen, and it is going to be connected to oxygen in this manner. Now this gives you a vinyl silyl ether, which is stable. You all know that this is stable, and it has been used repeatedly for the formation of the enolates, basically. Yes. Now after this step we are surely able to say that there is not going to be any further reaction. Alright, so what just happened? Here we have a allyl cation. This is our allyl cation that we have. Yes, this is the allyl cation that we have, and after this step where there is O minus, it is attacking over silicon. One of the hydrides is going to be lost, and that hydride is going to attack on the carbocation, and you get your hydrogen over here. So see, it's just the opposite that has happened. Here the hydrogen got added over here, and I have made a carbocation over here. So let's proceed with this, and you are going to get a product like this, which is basically the same. It is going to be the same as whatever is written over here. It's just the same only. So a methyl, a double bond, OSIME3, Si, alright, triethyl there is, yes, and a methyl and a hydrogen. This is what we get. Okay, this is what we get. Now further, no loss of proton from any of these two carbons makes the stereochemistry clear to us. Alright, and in the presence of an acid, what does happen in the presence of an acid? It is a proton donor, and since you have the enolate, it is going to attack in this manner. You get a ketone, yes, and the stereochemistry of one of the methyl group is going to be it's a mix, right? Above and below, it is a mix, because the enolate is planar. The electrophile could be taken away from the above as well as from the below. So I hope that you understand why is it written in a wiggly line, because we have a mix of above and below the plane in the molecule. Alright, so this is how you are able to understand that you are having the trans geometry because of the con-rotatory electrocyclization in the presence of the thermal conditions. Now this is the overall Nazarov cyclization. I hope that you understood each and every point that we have taken. Yes, right over here. It is acid-catalyzed electrocyclic formation of cyclopentenone from divinyl ketone. Desilylation is generally preferred over deprotonation. The Nazarov cyclization is 4-electron cyclization and occurs thermally by a Kohn rotatory process, and that is why it gives you trans product. Now that trans product is only observed when you are not forming a double bond inside the ring. How are you going to observe this? No carbon-carbon double bond, endo. No endo double bond. You might have a exo double bond like the carbonyl that we checked out, but no endo double bond. Then only you will be able to observe the trans geometry. Okay, so I hope that this was a lot of stuff about the Nazarov cyclization. Once again, reminding you all that I am also providing full-time, I'm a full-time educator on the Unacademy, and I'm teaching for the CSIR UGC NET category for chemical sciences. So if you want to join me on Unacademy Plus for the covering the syllabus, basically syllabus and the previous year questions that we do, syllabus revision, practice, everything, then you can use the code JAGRITI-S. Yes, you have to join through a referral code so that you get a 10% discount. Alright, so yes, you can join me up over there with the code JAGRITI-S for this 10% discount. And I hope that you also like this video. Do give it a big thumbs up. Also share it with your friends if you think that the content is good and it's helping you, and also since it is free, so it must be shared. Thank you so much, and also subscribe if you already haven't, and I'll see you very soon in the next video. Hopefully it is going to be out soon. Bye everyone, see you all very soon.